Welcome to third lecture for the week. Now, last lecture I was talking about the scale that is used for measuring sound. Because of a large range of amplitudes going from 10 power minus 5 to 10 pascals, we said we'll use a log scale. So the log scale is used, and of course a unit called decibel, which comes from Bell Laboratories in the US. Bell is basically 10 decibels, but the sound is usually measured, written as dB. You can see the small d and a capital B. The LP or sound pressure level is defined as 20 times log 10 PRMS by P reference. The PRMS is basically the root mean square acoustic pressure amplitude. So if you had a sine wave, for example, of let's say a peak to peak, that is it goes from say minus 1 to 1, then the amplitude of the sound wave is basically peak amplitude is 1, peak to peak will be 2, and RMS essentially in this case will be 1.4, which is root 2. So the reference sound pressure level is 20 micropascals, which is the threshold of human hearing. We saw last week. I'll again show you the range. You can see that 100 dB is like a construction site noise, very noisy. 130 is a jet taking off, whereas a typical conversation in a room, which is reasonably quiet, is about 60 dB. Alright, so we'll look at a little bit of human factors before we move to other things. Now, one of the things, as I said, constant exposure to sound can be damaging to human hearing. So therefore, how do you estimate from a human point of view the damage potential? So that means, obviously it's not just the amplitude, but also the exposure time. So we arrive at a metric called L equivalent, which is to kind of factors in the time of exposure. It's not simply the amplitude. So if I am just exposed to this sound for a short duration of time and nothing happens through the rest of the day, no big deal. But if I am continuously, I have to live with this all the time, this is going to be really terrible. So therefore, we define basically an L equivalent, which you can see is an integral. The integration 10 to the power of LP by 10 is actually P RMS square by P reference square, right? So if you look at, if you go back and do an anti-log, you will see that what is in that integral is basically a P RMS square by P reference square. So integrated over a period of time. Now this T can depend on the duration that you're interested in. In a factory, for example, it will be 8 hours is a typical shift. So you will probably come up with an L equivalent for that 8-hour shift. So this is kind of like averaging the energy exposure. P square is like energy. So we are averaging, we are taking that, integrating, summing that over the time, and then dividing by the total time of exposure. So it's kind of a mean RMS square or mean square energy over the averaged over the time interval which you are recording. And then of course we now take a 10 log base 10 instead of a 20, because it's already got a square in the integral. So this level is the equivalent sound pressure level. What is an awaiting? We will see shortly. Awaiting is basically a filter. The human hearing processes different frequencies. The sensitivity to different frequencies is different. Unlike a microphone which is used to pick up the sound designed by human beings, so it has a flat sensitivity, hopefully. Whereas your ear doesn't process in the same way. We will see that subsequently. So the LA equivalent is basically the A-weighted sound pressure level. We will see this shortly. Now in the US, OSHA, which is the Occupational Safety and Health Administration, has basically come up with what high levels, what is the LA equivalent that can cause hearing damage. So you can see here the exposure level here. This is called L equivalent, which is the exposure level. 85 dB is what you can be exposed to if for an 8-hour shift. Now obviously if this LA equivalent is 91 dB, then effectively you cannot be exposed to that more than 2 hours. So you can see that the amount of exposure that you can have if the amplitude is high is going to reduce drastically. So 94, for example, would mean only 1 hour of exposure. So this table kind of gives you what is the duration you can be exposed to if the amplitude is this, so that the LA equivalent is so once we calculate the LA equivalent, you go look at the table and then say how much time can you be exposed to this kind of amplitude. All right, this is how a factory worker would be, so a measurement will have to be done of the machines that are running over that factory shop floor, and once we get the L equivalent and LA equivalent, then we'll be able to determine whether we can have a 8-hour shift safely, or some other measures will have to be taken to keep it safe for the workers. All right, from a traffic noise, community noise, so typically when you live in the neighborhood and traffic noise, we basically have what is called as LN, which is the statistical measure, noise level, LN. So from a shop floor stuff, we have L equivalent, which is what is used to determine how safe it is to work for a certain number of hours. And for traffic or community noise, because these keep changing, right? So we have what are called as statistical levels. So L90 is simply a sound pressure level where the SPL is exceeded 90% of the measurement time, right? So that is kind of which means that it is at the lower level. Obviously, all the sound is above this 90% of the time. So I'll just show you a picture of a calculation. So here is a variation, sound pressure level variation over time. When I say 90, you can see here at the bottom, very small percentage of time the sound level goes below this. So L90 is kind of at the minimum. So what it means is 90% of the time I have higher noise level than this value. Here is the median level, which is L50, which is 50% of the time the sound is above, 50% of the time it is below. And of course, we use L10 as a measure, saying that 10% of the time it exceeds. This is at the top level. So the sound variation is kind of bracketed by the L90 and the L10, and L50 is kind of a median that we use to determine this. Okay, so this L90 is usually taken as a background noise level. So when we say that in my neighborhood the background noise level is 60 dB. So what it means is that 90% of the time the sound level is above 60 dB, and 10% of the time it is below that. Now L10 is, as I said, is the sound SPL exceeded 10% of the time, which is used as the maximum SPL. So if I now say 60 is L90 and 70, let us say, is my L10, so that is the maximum SPL that you would normally see in the neighborhood. And L50 is a median measure, so which may be 64 or 65 dB. Now these levels are used to define what are called as traffic noise. So most of the neighborhood noise, apart from machinery, typically in most places it is due to traffic. So we define what is called as a traffic noise index, which we will call, this is defined in papers as 4 times L10 minus L90 plus L90 minus 30 dB. Okay, now this is all done based on experiments and kind of an empirical curve fit. So there's a paper, I can give you the reference if you are interested as to where this is pulled out from. The so-called A-weighted levels, again something that we will come to, which accounts for human hearing, that is taken into account. And what they have found from this research, this traffic noise index, is a simple single figure that you can use, and it's found that there is a linear relationship between this traffic noise index and dissatisfaction. So Dissatisfaction, obviously 100% dissatisfaction means you are not satisfied at all. 50% means 50% people say, okay, I'm satisfied with this sound, and 50% are saying I'm dissatisfied with this. Now, for example, if L10 is 59 dB A, and A is added at the end of this to denote that we are using the scale, A scale. If I don't write an A, it means it is what is called as a Z scale. We will see all of these formally defined shortly. L90 is, let's say, 44 dBA. Then the traffic noise index, if you plug into that formula, happens to be 74. Now, a 74 index produces less than 3% dissatisfaction in hearing surveys. So, when these are, of course, it's a little bit of a what do you call qualitative measure. It's not a quantitative. So, you go and ask somebody, okay, these are expose them to these levels. How happy are you? And then if you sample 100 people, only 3 people say I'm not happy with these levels. So you have a target. So basically you say, all right, this is used in design of dwellings from roads. Of course, in India we tend to disregard any of these things. You plonk, I'm not sure which comes first, whether the dwellings come first followed by the roads, or the roads come first followed by the dwellings. In other countries, there's a lot of planning which is used to decide where should the dwellings be, so that there is less dissatisfaction. So of course, if it is not there, then we have to put noise barriers. We will look at some of these things a little bit later, so that if the road noise level is very high, for example, today IIT Bombay, to give an example, the dwellings existed before the roads. IIT Bombay happens to now reside on one of the busiest, what is called as Jogeshwari Vikhroli Link Road, JV Link Road. Earlier it used to be a small road. They decided to really make this into a really big road. With the result, the traffic density has increased, and now you see barriers outside on the walls of IIT Bombay to make life easy. So that is because the traffic noise index, the L10 and L90 levels would have gone up, and therefore they have to rescale to be able to serve the people, or get it to a level where people can tolerate that kind of noise level. So this is community noise. So we use what is called as traffic noise index, which is based on LN noise levels, L10, L50 and L90 levels. Please note that L10, L50, L90 are all applied to the same noise signal that has been measured. Last year we had, when it was without the pandemic, we had a small mini thing to do for MSB 358. But you can look at your own house, maybe sit outside and then see, okay, what is the kind of TNI for your, because you'll ask, where do I get a sound level meter? You could use unfortunately the microphone in the smartphones or whatever are not calibrated, but nevertheless you could kind of get a rough measurement done to see how the variation is, at least the dB level variation. There are various apps that are available. You can try that out to see what is the kind of difference between L10 and L90. Okay, so this is something that's there. So we have talked about the first criteria, which is at the factory level or workshop kind of scenario, which is the L equivalent, which is the exposure over time. L equivalent takes time into consideration. These are basically based on the noise that is being measured, the community noise, traffic noise index. Alright, then let's see, all these are measures, but ultimately to get all these measures done, we need to do measurements, and one of the key components of the measurement is basically a microphone. And there are basically 3 types of microphones. So what is shown here is basically a condenser microphone, and can also be an electret microphone. The bottom one is basically a piezo microphone. The condenser microphone is the one that is the most widely used, condenser, and now today electret microphones are widely used for acoustic measurements, high fidelity acoustic measurements. These things typically cost you quite a bit. Today Depending on the accuracy that you desire, this microphone along with the preamplifier, cables, etc. can cost you anywhere between say 75,000 to about 1.5 lakhs each microphone. Okay, whereas your cell phone microphone obviously cannot be more costly than the cell phone itself, right? So that puts in perspective, these things are very high fidelity, and that is why they are very expensive. The accuracy is quite high. All right, and so there are three types. So the way the condenser microphone, which is the most widely used, works is on the principle of capacitance, change of capacitance. The construction is quite simple. What is done is basically you have a very thin diaphragm, which is a stretched diaphragm, so it's like a membrane which is under tension. So the diaphragm basically acts as one of the capacitance plates, so-called capacitance plate, right? So in a capacitance you have two plates, so the diaphragm basically acts as one plate, and you have a back plate behind the diaphragm. All right. So this is the construction. Now the key part of this is the toughest part is to actually make that diaphragm, which is a thin diaphragm, keep tension, and the transducer lives forever. And this, of course, because it's a very thin diaphragm, if you put your finger on it, finished. So 1.5 lakhs down the drain. So to avoid that, we have a protection grid which is kept over that diaphragm. So you can see the slots are basically for the sound to enter through that protective grid. So the sound will come through that and then act on the diaphragm. Now obviously this diaphragm on the top sees basically both the acoustic pressure fluctuations, which we talked about, 20 micropascals to 10 pascals, but it also sees the atmospheric pressure acting on that, right? Now obviously this is a very thin diaphragm, it cannot take a 100 kilopascal force on it, but fortunately what happens is that there is a small vent behind the diaphragm. So what happens, the vent is so small that effectively behind the diaphragm I have only the atmospheric pressure. So the pressure fluctuations are filtered out because of the small vent. It acts as a what do you call it, basically a low pass, not a low pass, what do you call, a high pass filter. It will allow only above a certain frequency, or maybe it's a low pass filter. I'm confused between the two, but basically it acts as a filter. It blocks the fluctuations that is coming through, so only the static pressure can be seen, and all the pressure fluctuations are kind of filtered out. So on the top I have the mean pressure, which is 100 kilopascals plus pressure fluctuations. On the bottom I have only the mean atmospheric pressure. So on the top I have both of these, at the bottom I have only this. So therefore the effective pressure acting on the diaphragm is only the acoustic pressure. So that is a very useful technique by which, it's very innovative technique by which they are able to make a thin diaphragm and make it sensitive. So the measuring principle is basically the deflection of the diaphragm under pressure. So when the diaphragm deflects, it's a flexible plate, it changes the capacitance. I have a fixed plate behind that, which is this back plate, and I change the capacitance. Now this capacitance change, of course, will be converted into a voltage, and in order to do that, what is done is that we maintain a constant charge. Q is kept constant. This is done through what is called as a polarization voltage. So there is so these microphones, condenser microphones, need what is called as a polarization source, which is a DC voltage of 200 volts, which keeps the charge to be constant. So when I look at my voltage V equal to Q by C, you can see Q is held fixed. So therefore it is C which is changing. The delta C creates a delta V. So, and we simply now have, if we calibrate that to the pressure, the sensitivity, we know the pressure to, so if I apply what does 100 millivolts correspond to what pressure, then therefore we now have a sensitivity. Typically the sensitivity, I'll show you some catalog pages. Sensitivity is quite low in the sense it will be probably in the order of about 20 to 30 millivolts per Pascal. So this is a condenser microphone, and The electret microphone is a new device. What is done is that the diaphragm carries the charge. So it's a charged diaphragm. So they call it an electret from electrical engineering technology. So therefore the polarization voltage is not required. So these are called electret or zero polarization microphones, and they work similar to, otherwise the principle is the same. The capacitance change reflects as a voltage change. Alright. So let's see. Alright, so let me probably do one or two more slides before I end this particular lecture. The selection of, so the trouble with this is microphones, if you go to a manufacturing catalog, I mean the catalog available with a company like Bruel and Care, which is a very well-known company in making acoustic microphones, you will see that they will ask you whether you want a free field microphone, random incidence microphone, or a pressure microphone. So there are these three categories. The free field is basically most accurate for sound from a single direction and single source. So if there's a dominant source which is creating sound and it appears to come from a single direction, then this microphone is very useful. Now free field by definition means there are no reflections. So if you were standing, for example, in a cricket ground, still finite, but the dimensions are so large that if I create a sound, it has to travel quite far before it gets reflected. So therefore it's almost like there is no reflection, right? So that kind of scenario is called the free field. Now opposite of this is where there are infinite reflections, so multiple reflections. So with no reflection is free field. Multiple reflection is basically what is called as a diffuse field. Diffuse means it is reflecting from all directions, so you have no idea where the sound source is. You turn your ear everywhere, you will be saying where is the sound coming from. So it's completely diffuse. So these type of microphones, the free field microphones that are available in the catalog, work best in open areas where there are not many reflective surfaces present, and these are used in what are called as anechoic chambers, or in large open areas. We'll talk about what an anechoic chamber is a little bit later. Then you have what are called as pressure field microphones. So these are designed for sound pressures that exist in front of the diaphragm, usually for doing measurements in an enclosure or a cavity. So if I'm interested, for example, in a car cabin, so I can mount these on the wall and then measure what is the acoustic field within the car cabin, because I'm interested in reducing sound inside the car cabin. So in that kind of scenarios, you don't put a free field microphone on the wall, you will put these pressure field microphones. And the last one is basically a random incidence microphone, which is designed to be omnidirectional. It says, so I told you a diffuse field, the sound comes from, it appears as though it comes from everywhere. This microphone is designed to measure such type of things where the sound can come from anywhere. So if you have multiple sources in a room, or sound appears to come from multiple directions, then this is the kind of microphone that you need to use. So so when you buy or when you decide what kind of microphone you want to use, you will have to either a free field microphone if predominantly sound seems to be coming from a particular direction, or you are in large spaces where there are not too many reflections, then a free field microphone is very useful. If you are going to do measurements in car cabins or and mount microphones on the wall, then a pressure microphone is used. Otherwise, if there are multiple sources and the sound appears to come from different directions, then a random incidence microphone is the best that you need to use. I think we'll stop at this point with this lecture. We will proceed further in the next lecture.